Hey guys, okay, so this is the midterm one walkthrough. I just want to go through a detailed discussion of each question, how to attempt it, and just some other explanations. Okay, so for question one, we're going through a large molecule. We're asked to recognize certain functional groups and other components. So first of all, taking the first one, the carbonyl is part of what functional group? Remember, the carbonyl is a fragment that's a carbon double bonded oxygen where you can have different things attaching to these other sides. Depending on what's at these positions, it changes the function or the name of the functional group. So carbonyl is just an important piece, but it really depends on what's around it. That's what changes its name. So if you look through this molecule, carbonyl is right here. That is not a carbonyl. That is a carbon double bonded nitrogen. This is my carbonyl. If that's my carbonyl, carbonyl is part of oxygen on one side, carbon the other. That is an ester functional group. Second one, the nitrogen atom is part of what functional group? So if you look through the molecule, there's a nitrogen right here. The functional group it's a part of is this entire chunk. This is my oxime. It's not just an imine, it's an oxime because we have an oxygen on that side. How many asymmetric centers are present in the molecule, which means I'm saying chiral atoms or point to chirality. The other way to look at this is any center that you could assign as either R or S. We're not saying it's one or the other, it just has an R or S designation. So to do something like this, what you're generally going to do is scan through the molecule and you're checking each center to say, does it have 4 different groups with respect to CIP priority? So this one counts here, 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 and there. There are a total of 1, 2, 3, 4, 5, 6, 7, 8 individual chiral centers in this overall molecule. 9 right there. Thank you. So 9 molecules in this case. Now just note that just because it's drawn as a wedge or a dash doesn't necessarily mean it's chiral. You should check each center to see if they have different CIP rankings. So for example, a molecule that might have flat, but if I were just drew a molecule like this, like a methyl right there, that's still a chiral center, it's just not designated as R or S in that particular geometry. How many E alkenes are present? Remember, E alkenes are molecules where the highest priority groups are on opposite sides. Z is on the same side. So highest priority groups with opposite, there are 1 E alkyne here, that's this one and this one, high priority. 2 here and here, high priority. And that's highest priority. This is highest priority. There are 3 E alkenes across that. This one is actually a Z. Highest priority groups are on the same side. And this does not get an E or Z designation. This is an oxime, so we wouldn't give it necessarily, it's not an alkene in particular. So there's a total of 1, 2, 3. How many sp2 hybridized oxygen atoms are present? Now remember, to be sp2 hybridized, we're saying it's an oxygen that is either has a double bond or is part of a resonance isomer that reduces its hybridization to an sp2. So this one is already, because it has a pi system. Remember, there's a delocalization over here as well, so this one also potentially has that. The only other one, this guy right here, there's a resonance isomer where that will also be delocalized into it. So there's a total of 1, 2, 3 oxygens with our sp2 hybridization. This one is not, this one is not, this one is not, because there's no resonance contribution by the lone pair. Okay, for question 2, we're asked to look at this compound under acid catalyst conditions and basically hydrolyze it. We're asked to break this compound down to draw the linear form of this once it can open up. Now, in this molecule, this is similar to a couple questions we provided on the problem set. If you notice, you should recognize this as a carbohydrate. More importantly, we have alcohols at centers like this. This center is unique though because we have a carbon attaching to 2 oxygens. That is a hemiacetal versus a compound like this center here, this carbon, 2 oxygens. This is your acetal. So those are the ones that are different among the entire centers. This center here is a hemiacetal. This center here is a acetal. Both of those are susceptible to be hydrolyzed under acid conditions. So there's actually 2 centers that can hydrolyze, but let's take this one at a time. Let's actually take this one first, only because if you notice, we sort of have a compound where we have 1, 2, 3, 4, 5 centers. Then we're bridging with this oxygen, and we have another 1, 2, 3, 4, 5 centers. And if you look closely, hemiacetal, or this sort of aldehyde-like center, it's effectively a carbonyl that's now been collapsed in with 2 oxygens. We have 2 of those, and if you count them out, carbons 1 matches with carbon 1, carbon 2 matches carbon 2, 3 matches with 3, 4 matches 4, and then finally 5 matches 5. They both are 5 carbon units, so this is starting to look like potentially 2 separate 5 carbon chains if you kind of treat them individually. So I'm going to hydrolyze at this center first, and when you do that, remember, if you do your acid catalysis, just focus on this. Remember, the general mechanism for acid hydrolysis of an acetal is going to go through a process where protons plus water is going to split off one of those groups. We're going to lose one of those fragments. Let's call this our sort of our prime, one of those alcohols, and that's going to result in OR, OH, and an alcohol, right? Cutting that group off with water will hydrolyze that center, and we end up with 2 separate fragments across this one. So applying that principle to what we're doing here, what we're really saying is between, let me just get some of this, focus in. If I'm going to hydrolyze this bond, this center here is my carbonyl, effectively. It's the carbon attached to 2 oxygens. This is my alcohol. So in other words, that center is like my OR. This center here is my carbon center, part of my acetal. So hydrolyzing across that center is going to split it like this, where that center will be like this, and your alcohol piece is your alcohol piece. So redrawing that strictly, I'm just going to redraw that point. Cutting across this bond, I'm going to have 1 molecule, and for now let's just leave everything, geometry, everything else in the same place. OH, this is still a wedge, OH, this is still a wedge, OH, this is dash, OH, like this. And on the other side, we have alcohol to a wedge. We have our 5-membered ring, double dash OH, and leave that one as it is, OH here. So now we have 2 5-carbon units. Again, just pointing out common similarity between the 2. This first ring carbon here is a hemiacetal in both cases. Then we have 2 oxygens, which are syn to each other, and we have, opposite from that, this CH2OH branching off at that point. So what we can do, though, is if I take this molecule and I undergo a pancake flip, I'm just going to flip it end over end, right? So numbering this off, carbons 1, 2, 3, 4, and 5 will now look like, pointing it the other way, OH dash OH, OH, and wedge OH, where again numbering those off, that's carbon 1, 2, 3, 4, and 5. So all I've done is just flip it over, and if you look, these are now identical except for the geometry at the center. That's fine, because remember, if we hydrolyze this further, this is here is a hemiacetal in both cases. That's my hemiacetal center there and there. The hemiacetal, just generically again, if I show you what this might look like in a more simplified form, the hemiacetal with proton and water will hydrolyze back to the alcohol fragment, and in this case, since the other functional group or the other atom is a hydrogen in both of these cases, that means that we have a aldehyde at that point. Really, this is just a masked aldehyde center in both of those two. So hydrolyzing these ones, we're going to be cutting this bond over here. It will remove that chirality because we're going from a sp3 tetrahedral carbon back to an sp2 planar carbon. So redrawing that, and I'm only going to do it once just because these are both identical in this case. That first hydrolysis gives us two molecules which are just identical fragments. I'm going to redraw. No, let's do this one. Getting rid of this one right now because, again, just think of it where we have two of the identical molecule. Hydrolyzing this, and we're not going to straighten it out quite yet. We're going to leave everything else common, so that becomes OH. Over here, aldehyde. Dash OH, dash OH, and OH. And again, numbering those off. Carbons 1, 2, 3, 4, 5 corresponds to carbons 1, 2, 3, 4, and 5. So we have two molecules of this now linear aldehyde. If we want to straighten it out, where we just have it in the backbone, is going to look like a zigzag kind of form, something more like a normal line bond. We could redraw this as our aldehyde on carbon number 1. Carbon 2 is going to have dash OH. That's the same geometry we have over here. By rotating around, when it's syn in this kind of geometry, it'll end up as anti when we go back to this kind of more conventional linear. Likewise, this will be OH, and then finally, like that, we'll put the carbon in plane. So that corresponds to carbon 1, 2, 3, 4, and 5. So this is both using spatial recognition when you rotate it in your mind, or, as I've mentioned before, you can assign RNS notation to the carbons, and that'll also help you as well. But effectively, we end up with two molecules of this particular geometry by this hydrolysis. So for this question, we're asked to indicate with a yes or no if sodium methoxide, so remember that's our OMe minus, that's the base that we're considering, is a strong enough base to irreversibly remove the proton, the most acidic proton in each of these compounds. So step one is let's identify which proton we're probably talking about. So here it's this OH, this is the CH right here, this would be one of these CHs over here, this is the NH, this OH, and this OH. Those are the centers we're dealing with. Now, this is really a question about relative pKa. So what we're saying is, if I was to take, let's look at each of them. This is actually a method that we apply in Chem 123. So if I'm going to evaluate the first one, what I'm saying is, if I took this molecule, this OH here, and I treated it with my base, I will be in equilibrium with the conjugate base, in this case O minus, and the conjugate acid, methanol. And if I'm going to determine which one is irreversibly deprotonated, what I'm saying is it has to completely deprotonate, completely favor. So usually that's something we're within about 2 pKa units of the different respective acids. So remember, methanol has what pKa? That's the conjugate acid of the base that we're evaluating. Methanol has a pKa of approximately 16. Phenol, because it's an alcohol, that would sort of be in that 15, but it drops by about 5 pKa units. It's in the round of sort of 9 or 10 at that case, just because of the stabilization due to aromaticity. So now here are my two pKa's. pKa of 9 for this acid, pKa of 16 for this acid. That means that that acid will push a lot harder. The equilibrium will lie in favor of the products here. So this would be yes. And again, that's just a difference that the two acids I'm evaluating here, their relative pKa's, are significantly far from each other, forcing it to favor deprotonation, forming methanol. We can do that for each of these particular compounds. Now, if you remember, the relative pKs of each of these, alpha center of the alpha center of the CH, this is somewhere in and around 20. That's no. This one is going to be about 21 to 25-ish, depending, because it's alpha to a carbonyl. No. This NH, this is around like 35. Think like LDA, right? So lithium, like the deprotonating a neutral nitrogen is very high. That's known. This pK is in around 0. It's a very acidic center. Yes. And this is our standard carboxylic acid. So pK about 5. Yes. Okay, so question 4. We're asked to take Newman projection of some Wittig reagent carbonyl addition. So this is the first addition component after adding a Wittig reagent to an aldehyde in this case. You can tell that because you have a hydrogen, carbon, and this oxygen, so we must have added to an aldehyde fragment. What we're asked to do is complete the Newman projection of the molecule as it starts to produce the oxophosphatane. Remember, this is the betaine, this is the first addition material. If it's going to go through the elimination, what we have to do is this oxygen and that phosphorus need to be located close to each other in a eclipsing relationship. So the main thing we're doing here is we're rotating that phosphorus and oxygen, the plus and minus together, so that they can do that elimination to make our double bond. That's number 1. Now what we're doing really is just rotating each of the rear atoms around into an eclipsing relationship to the one on the front, which means we don't have to touch anything on the front. This position at the front, the isopropyl, remains constant, and the methyl remains constant. Actually, let me just do that in a different color so it's a little bit more obvious. This is our isopropyl corresponding to this group here, and then we have our methyl over here. Okay, now on the back carbon, since we're rotating the oxygen up to this position, eclipsing that phosphorus, what it means is over here, we're going to have a hydrogen. That's just a result of moving that hydrogen down here. And then this is our cyclopentyl. So that's going to be 5-membered ring like this. And notice what that's doing is we're starting off in a geometry over here where the two largest groups are anti to each other. That's common for our Wittig because this is the first addition product. That's our the betaine. However, when it rotates around, it's putting those two large groups now very close to each other. Now that means for the final product, what we're going to do is eliminate. We're going to eliminate this part over here. That gives us our triphenylphosphine. So I'm just going to put that over here. Triphenylphosphine oxide is one product. That's not the major thing we're looking at. What we're trying to identify is the carbon-containing alkene. That's the result over here. So you can see what we're doing is we're sighting down that bond. It means we're going to have a carbon-carbon double bond, where let's say this was this front carbon. We were originally looking at making this one the rear carbon, the one in behind there that we can't see at the moment. Again, you could choose any direction that you prefer, but for now, let me just sort of indicate it according to that. Front carbon right here corresponds to this carbon right here. That front carbon is going to have two things attaching to it. It's going to have an isopropyl and a methyl. The rear carbon, the one in the back over here, its constituents are going to include a hydrogen and a cyclopentyl. Most importantly, isopropyl and cyclopentyl are on the same side relative to each other. That's the consequence of doing a Wittig reaction. The two bulky groups end up cis. And then on the back one, we've got our hydrogen. So this will be the final product that we're generating over here. For this question, we're asked to form the major enolate after deprotonation under the conditions applied. And if you notice, what we have is a molecule where we have several alpha protons, 2 here and 1 there. And what we're asked is under these conditions, LDA, minus 78 degrees, that is our classic kinetic deprotonation conditions. It will pick the least substituted center, deprotonating there efficiently. So we're going to have our product. The enolate can be drawn in one of two resonance structures. Either we're going to have it drawn like this. We have a negative charge over here, and notice that we have not touched the chirality or anything about the methyl center over there. So that's this one. The other correct way to potentially draw this is as the carbon-carbon double bond, so the oxygen-centered enolate. That is also a correct orientation. Either of those two is okay. And the other conditions, sodium hydride under heat, that is our thermodynamic deprotonation. That's where what we're going to do is target this other center over here. So major things we have to do, this is both the location that we're deprotonating, but more importantly, we're also destroying chirality. When we do this, although this had a defined chiral center, as soon as we deprotonate like that, we're actually going to be losing that. The reason why is that anion center is not an sp3 center. Remember the resonance isomer, if we were to draw it in the other geometry or the other conformation sort of thing, other resonance isomer is a double bond across here, really showing you that that carbon is actually a planar sp2 center. Okay, for this next set, we're asked to carry out a series of reactions. We're giving your starting materials and the products. So this forces you to go through and locate the reaction conditions in order to execute these. So starting out here, we're going from a molecule to new functional group. This is your imine. Imine is created by taking your nitrogen and your carbonyl. Notice this is 1, 2, 3, 4, 5, 6 atoms away. That gives you a 6 carbon center. This would be carbon 2, nitrogen 1, carbon 3, 4, 5, and 6. Carbon 3, notice, has a stereocenter and has the exact same stereocenter. The only thing we're doing here is providing a weak acid catalyst. So you can say proton catalytically, it would be acceptable to give you a specific proton like HCl under catalytic conditions. Most important is that it has to be an acidic catalyst and it has to be catalytic, not stoichiometric. Okay, next conditions here. If you look at your transformation, we are starting off with a fragment. Remember, this is our ketal, actually, at this center, and we're forming an oxime over here. This cannot be transformed in a single reaction because we're doing a couple different things. First thing we have to do is actually expose the ketone at this point. So this would be proton acid catalyst, but more importantly, we need to have water present. If we don't have water, we're not going to be opening up this ring, because in the end, we're going to be making a fragment like this. So that's carbon 2 right here, which corresponded there to carbon number 2. From that one, we're going to go and actually add in our oxime. We're doing a condensation. So this is similar to an imine formation. We need the nitrogen fragment, which is NH2OH. And again, we're going to need some type of acid catalyst in order to make this happen. So we're going to be forming like an imine condensation. Now we're stripping the water back out to make this geometry. In this compound here, once again, we're doing a transformation. If you notice your structures, your product identifying it, this center here probably corresponds to that. We've got two different geometries. This center here corresponds to that center, which also makes this one probably correspond to that carbon there. So those are the kind of the geometries we're setting up. If you notice, what we've really done is we've gone from 2 carbonyls into 2 alcohols. And the major difference between these two, it's not so much this red center. The red center is identical in both of those two. Big difference here is that this blue center, one of them, we've got a hydrogen up in this position. The other one, we have a hydrogen in the equatorial plane. So there's 2 different diastereomers at that center, effectively. So in order to do that, we're going to have to do a reduction. That's how we first convert this to the right oxidation state, because what we have is we're missing some hydrogens, basically, that should be present at both of those centers. So that can be done simply with something like sodium borohydride. You don't need anything harder than that. Now, if you use something like lithium aluminum hydride, it's not incorrect. It's just kind of overkill. Sodium borohydride will not get us the product directly. That gets us our first step. What that's going to do is produce a mixture of our products where we have this and the other potential geometry, OH, where like that. Remember, the only two major differences we've seen, because we're not doing any reduction at the second center. This one is staying the same. This is where we're doing that reduction at this top one. So the two different geometries correspond to two different approaches of our hydride from either the top or bottom face of that center. Now to get it to close, you notice what we're missing now is this acetal. So we need to add in both the carbon fragment necessary. That's going to be something like acetone. It's a 3-carbon center where this middle carbon right here corresponds to that carbonyl, and it's going to be done under, again, acid catalyst. Most important too is again, catalytic acid. Do not use water. Water is not present in this one. That would hydrolyze this. This is something where we're actually trying to remove water from the system, so you could use a Dean-Stark trap or some other component where acid catalyst is necessary. For this next one, what we're doing is you can see the core molecule that we have here is represented there, which means we're making this new nitrogen to carbon bond. It means all of this is new fragment. And more importantly, look at where the deuterium is being incorporated. We're bringing the deuterium at that center over here. So it looks kind of like, again, a two-step type process. What we have to do is, first of all, this fragment is going to be carbonyl containing compound where we have a methyl corresponding to out here, the actual carbon center itself, and then the benzene ring. So this is sort of this acetophenone type compound. It's a carbonyl in the middle as a ketone where we've got this methyl carbon and then aromatic ring. That's what this fragment would basically correspond to. Now if you just put these two fragments together, you would get this imine. That's not the product yet, but if you notice, this center here, this is our delta minus kind of center, and as a result of that, if we took a molecule like D2O, D2O is equivalent to deuterium plus. That's going to locate itself on this nitrogen, because what we're doing here effectively is reductive amination, right? What we're doing is going to do this condensation and then reduce this, more specifically reducing the iminium form of that, where protonation in the middle of this will give you iminium, which is now going to be accepting a hydride nucleophile at that center. However, this here, adding to the center, we notice we've been told it's a deuterium, so it's not adding hydride, it is adding deuteride or nucleophilic deuterium. So to do this reaction, we're going to need two parts. Overall, I need to have my carbon fragment, so that's the first reagent that I have to include, and I'm also going to be doing this under some kind of acid catalyst. Protons for H+, that's because we have protons attached over here, and we need our sodium boro DCN3, something where we're using that weaker or more specific reduction system in order to get this kind of reduction reaction to work. So it's the sodium boro deuteride in this case, where it's the deuterium from this electron withdrawing kind of system like this. All right, now for this reaction, notice we're doing two parts. We've laid it out so you can kind of see the same centers. This carbon here now has a carbonyl attaching to it. This center here, same chirality, except we are now missing a carbonyl at that center. So this goes back to some of the reactions we're talking about the selection of what might be compatible. We have to, at some point, probably create a nucleophilic center over here. This could be something like creating a Grignard reaction or at some other point. And if we had a Grignard reaction at the center, we could probably add CO2. That'll give us this carbon fragment. However, we do not want to do the Grignard addition or magnesium formation. First, it has to be second, because if we make a nucleophilic center here while that carbonyl is still present, we're actually going to get cross-reactivity. First thing we actually want to do is reduce that or blow away the carbonyl. Remember, we have two conditions for that, the Clemmensen reaction and the Wolff-Kishner. We are going to use the Clemmensen. That's our zinc, magnesium under acidic conditions. The reason for that is because if I use something Wolff-Kishner, remember Wolff-Kishner is nucleophilic, something like hydroxide and hydrazine, that'll actually attack this center here. So we're going in with our acidic conditions that will remove this center first. Then, second step, we come in with our magnesium and our CO2. And again, we're doing nucleophilic conditions after I've removed that carbonyl to prevent any other reactivity. Okay, so for this reaction, what we're going to do is put together these components, look at these conditions here, and if you've got to recognize, first reagent we're doing is triphenylphosphine, then we're adding a strong base, and then we're bringing in a carbonyl component. That sequence is our standard Wittig type chemistry. So after step 1, we are going to make triphenylphosphine type reagent. So we're doing PPH3, and this will be plus at that time. So after this addition, we're still going to have the proton here. After step 2, we're removing that proton, creating the nucleophilic center at that point too. So that's what we're doing here. After step 3 now we're doing a nucleophilic addition. Now notice this is our standard Wittig reaction, which means I'm going to make a double bond between that carbonyl and this nucleophilic center. So I'm going to just start by sketching that out first. I'm going to make a new carbon-carbon double bond, and it's going to be between that pink carbon and what we had as our green carbon. That's what's happening between the two. And the constituents, the components are still coming in. On the pink carbon, we have two groups. We have a methyl, and we have the cyclohexyl, the six-membered ring. If we do this and just drawing up that point, now I've defined two different geometries. On this side, I have a methyl and then this large ring. Remember, this is unstabilized, which means we're following standard Wittig type conditions. I'm going to bring in the small groups. So this methyl and the other methyl will be syn to each other, making the two large groups syn to each other. It's going to be identical in terms of geometry that we started off. So everything you saw coming in as a payload will look the same. So it's still got that same wedge, it's still got that oxygen. So the two rings are going to be close to each other. All right, under these conditions, what we have here is a nitrile at the alpha position. We've got acid and water at high temperature. These look like protonation and hydrolysis. And anytime you've got acid, that might be a simple workup, but acid plus water plus heat, that's going to be a hydrolysis where we're actually changing the structure. So those are things like esters, amides, or in this case, hydrolyzing the nitrile. So if we do this, remember that's going to convert that nitrile through a couple of different stages. First off, we're going to start off with this. If we add just one molecule of water, the nitrile is actually going to convert to our primary amide. That's the first step. But keep heating it, more water, we're under acidic conditions. That's actually going to take the primary amide down to carboxylic acid. That's where we eventually end up to. That's the standard conditions for things like the Strecker reaction when we're hydrolyzing these amides. It gets you down to this guy. Now notice the geometry we have here is this standard 1-3 geometry. The other way I could actually draw this to emphasize it is that. This is our standard pericyclic reaction decarboxylation. So that'll give you, at least initially, the enol form, which then rapidly tautomerizes back to our keto form. So the hydrolysis we do on this point, having that nitrile in that position, will take us all the way down to the carboxylic acid, but since we're using acid and heat, we can continue through losing CO2 to give us our final product. Now, in this one, what we have is simple acid, and we're specifically telling you you're losing water as we do this. That's what we're trying to indicate in this, that there was a loss of water as you go through it. So this is a condensation reaction. At this time, remember, you've got your nitrogen, and if we're doing a condensation, collapsing a nitrogen under acidic conditions is our classic imine forming condition or enamine forming condition. Same type point. You notice this is a secondary amine, so we're probably going to collapse into either one or the other carbonyl to make our iminium, and then we're going to lose another proton. So the first task we have to do is, okay, I've identified my nucleophilic nitrogen. I have 2 possible carbonyls. Carbonyl 1 over here is 1, 2, 3, 4, 5 atoms away from that nitrogen. Going the other way, carbonyl 2, 1, 2, 3, 4, 5, 6. This is a 6 atom away point. The 6-membered ring is going to be more stable than the 5-membered ring, even though the 5-membered ring may form, let's say, faster, but thermodynamically, the 6-membered ring is going to win. So based on that geometry, I'm just going to show the iminium first. So we're going to draw the ring, the rest of the atom, where we're not touching this OMe, we're not touching that carbonyl. We have the same relative geometry here and here right now, and we're making a 6-membered ring down to this external carbon. This is carbon number 1, 2, 3, 4, 5, and 6. 6 atom and number 6 being our nitrogen in this case. That's being bonded back to carbon 1. Now, nitrogen 6 also has a methyl attached to it, and if we were to draw this as that sort of normal condensation product to what used to be this carbonyl on this, or this aldehyde-like center over here, that's going to be our iminium form. So now that we have the iminium, that's one product. However, what we have to do is form the enamine. Remember, secondary amines like this, when they condense into the carbonyl, can form our enamine. That enamine is going to have a geometry where you've got this proton over here. Deprotonating here is going to make a double bond across that center and then reduce this to a single bond. So what that looks like as the more stable, uncharged molecule will be a 6-membered ring like this, where we have the rest of the 5-membered ring appended to it. Oops. That and OMe. So again, numbering things off, this is carbon 1, 2, 3, 4, 5, and nitrogen number 6. We now have removed the chirality over here. It's dropped down from an sp3 to an sp2, and we've now made our final molecule like this. Okay, now in this case, we're adding excess bromine and sodium hydroxide under acidic, under basic aqueous conditions. So this allows us to form enamines, or enolates first, excuse me. So we can deprotonate anywhere that we have an alpha proton. So if you look at this molecule, we have alpha protons here for one, and we have alpha protons over here. Just in general, these ones are kinetically favored under basic conditions. Deprotonating at those green centers are probably what's going to happen first. And if we carry that part out, what we're going to get is bromination initially at that green site. So that's going to go through a process of, first of all, enolate formation. I'll just show you this first kind of sequence. It's going to go sort of one at a time. So enolate formation over there, then bromination, we have a single bromine, and after that, since we have a single bromine, 2 more protons, this is far more acidic than any other molecule or any other proton in the system. The second 2 brominations will happen rapidly by a similar pathway, giving us the tri-brominated product. Now, as soon as we're there, this carbonyl is going to be quite electrophilic. Nucleophilic attack of our hydroxide at the center gives us the bromoform type reaction, which allows us to convert that center into an alcohol. Now, one interesting thing, as soon as we do this, there's kind of 2 reasons that we select for this particular product over anything else. First, this center is kinetic. Deprotonating there first gets us our first bromine. The rest of the bromines nucleophilic attack, and then into the carboxylic acid. So one of the questions we did receive is, well, wait a minute, why don't we just brominate over here? You know, you can recognize that this methyl group over here is connected via resonance over to that sort of site. Now the conjugate addition one, or this particular deprotonation, alpha to the carbonyl directly attached is still going to be faster than one that's remote over here. And more importantly, once we've done this, once you've actually gone through this sequence, and you make this first carboxylic acid, under the strongly basic conditions, it's going to exist as the carboxylate. Once it's negatively charged, these protons are no longer acidic, because deprotonating there would then push another negative charge next to what is already charged over here. The installation of that carboxylate effectively protects that other methyl, so it's really only that first one that happens. But we do still have these two over here. They can undergo a similar dibromination. The difference here is we add 2 bromines. Because we can't add a third, cleaving this bond over here is actually quite difficult. So we end up making simply the molecule after workup, reprotonating it. We end up with this dibromination over here and the carboxylic acid over there, one from the bromoform reaction and one from just simply alpha bromination of the carbonyl. Okay. So this is our deuterium question. This is where we're looking at potential exchangeable sites of the molecule. We're actually adding a couple pieces in. So there's 3 different layers to sort of look at this one. First off, and this is based off of one of the questions we had in our problem set. We have 2 protons over here. These ones are directly alpha to the carbonyl. These are the ones you should easily be able to form. That's the first sort of pair of bromines we should be looking for. Or sorry, bromines, protons that we should be looking for. So deuterating at that first site should be the easy ones for you to identify. Next, because we have this conjugate pathway over here, notice that this here, effectively, yes, it's an imine, but that imine is really not much different than a simple other carbonyl. Those 2 protons over here are also available. They're just alpha to, it could be this other carbonyl. We'll come back to that one in just in a second. But notice what we have is there's 2 more protons over here, and I'm going to highlight actually 2 more over here just for that point. Notice if in this geometry of how we've got the centers lined up, if I was to deprotonate over here, that resonant negative charge, if I draw out that structure, or again, I know it's under acidic conditions, but you can think of it very similar. Let's say I protonate this, this carbon over here, the oxygen over here. I've got a geometry that looks like this. So protonating over there, I've got these 2 protons over here. Because of this pattern, I can actually take a base, or water in this case, something that can pick up that proton. Because we've protonated over here, I can now tautomerize effectively in a pattern like this to give me an extended enol structure like that. All that just means is these 2 protons down here can be exchanged under acidic conditions because they're connected by way of this double bond back to the original carbonyl. Likewise, you can do the same sort of mechanism by protonating here and deprotonating over there, and protonating here and deprotonating over there. All those are sort of possible in terms of your alpha-beta exchange sites. However, these 2 are not available. Protonating at either the oxygen or the nitrogen, as we've drawn over here, there's no way to pull these protons by how the pattern of where our double bonds are, or to stabilize either a positive charge or negative charge. These are not in the right position for the resonance structures that we're dealing with. So these do not exchange effectively. So we've just identified 3 possible centers for exchange. These 2 over here, these 2 over here by conjugation, these 2 over here because effectively we are alpha to effectively what is a carbonyl. It's just drawn as an imine right now. So there's only one more. If you were able to go through and identify that those 3 sites are your sites for deuteration, good job. That's most of this question. So that would look like this, where we have 2 deuteriums here, 2 deuteriums here, and 2 deuteriums here. Those are your exchangeable centers. There's one more thing to watch out here. Look at these conditions. This is acidic water. Under acidic water, molecules like imines are susceptible to hydrolysis. So that's where you can clip this bond, breaking it back into their original structures. And if we did that, just hydrolyzing that point, that's going to give us, at least initially, hydrolyzed molecule, which frees up our aldehyde. So again, deuterium's here and here. That would give you a nitrogen double bond, and our deuterium's at the sites we've already identified. So NH2 or ND2 in this case. Remember though that is now our enamine. The enamine in the presence of water can further hydrolyze. That gets us back eventually to either a carbonyl or an enol. So the final molecule could be drawn either as something like this, where we have two deuteriums, and two here. And in this geometry, we've got those two as well. Now, in this particular one, you can draw this where it's this sort of diketo form. Notice that that proton is sitting in between these two carbonyls. That can exchange. Or you can draw it as we have in the answer key, where we're going to draw this not as the diketo form because it has the possibility of having a resonance stabilization. The other way we would potentially draw it is one of these is in their enol form, and that's not an OH, but an OD. So effectively it's just a tautomerism from the structure that I showed you over there. So that's our final part two, if you really could capture all the pieces. Okay, so this is a multi-step transformation. We've given you reaction conditions and we're asking you to carry out this transformation. First step, you have to look through each component and look what actually changes. So we're going from a primary alcohol to a carboxylic acid. That is uniquely our Jones reagent. That's where we're doing this oxidation at this center, so Jones is the correct one to choose. Once we have this carboxylic acid, we are going to this molecule. Notice we have a carboxylic acid and we're losing it, and it's in that 1,3 relationship to this carbonyl. We need two things for that to happen. We need protons, and more importantly, we need heat. This has to happen with temperature. So one of two ones I would consider acceptable. It's probably better to focus exclusively on catalytic acid and heat. Those are the only two things you need. If you did choose something like acid, water, and heat, we thought acceptable. However, generally, water, it's also a nucleophile. Probably not a good idea to expose a molecule like this to that point. Really, the only two things we need is protons and heat to have this happen. By throwing in water as well, you open up the opportunity to potentially convert that to an alcohol by SN2. But we consider this acceptable. All right, so once you've got that one completed, now you've got this molecule. Next step is we have to do something plus this. Notice what we're doing is we're converting that carbonyl into a ketal. So that's strictly where we need acid. Now again, acid or acid and heat could be possible under these ones. Best conditions is probably just acidic treatment and then following it with this alcohol. This is wrong in this case because if you start doing that condition in the presence of water, you're not going to form your ketal. You need to remove water from the system, so it's not appropriate to do water, acid, and heat in this case. The simplest one would probably just be catalytic acid. All right, moving forward from this one, we're taking this molecule, treating it under some conditions, and adding a formaldehyde. We're adding just a single carbon across this. So if you look at your product here, we're now extending it by one carbon. We're taking what used to be this benzoyl bromide, and we're now one carbon longer in order to get to our final product. So going through your conditions here, this is where we have to do some kind of an addition reaction in order to get this, this product together. Now, it means that we're probably going to be taking a nucleophile in this case here and adding it to this electrophile. Effectively, we're just doing something like that and then work up to get us this compound over here. So what we're doing there is we're converting that benzoyl bromide to a nucleophilic center using magnesium and then adding this aldehyde to it. The aldehyde becomes a primary alcohol in that case. So magnesium is the correct choice here. Once we're here, we're doing conversion. Notice we're just doing an oxidation stage adjustment. We're going from a primary alcohol to an aldehyde. So Jones is not what we want to use in this case. We need to use something lighter. That is our pyridinium chlorochromate. That's where we're doing just the oxidation to the aldehyde. Once we have the aldehyde, we now want to invert these two. We want to open back up this component, so we now have to hydrolyze this. This is where we need to use acid and water. So we want to do this hydrolysis reaction. Protons are important, but we also want to bring water in so that we can clip off that alcohol. Okay, now that we've got two of our carbonyls present, we're going to go back and similar conditions as before, same protecting group as before. Difference now is that since we have two carbonyls, the aldehyde is more reactive. All we have to do is go and use our catalytic acid conditions again in order to form the acetal. The acetal will form preferentially just because it's more electrophilic than the ketone. Once that's present, look at what we're doing here. We're converting the remaining carbonyl into a carbon-carbon bond. So this is where what you have to do is something that looks like nucleophilic addition of this additional carbon. We need to bring something in. And there's really only two reagents that have a carbon-containing molecule, like a Wittig reagent. This one here has a single carbon. That's actually the correct one. This one here has a different structure. What we've actually got is a carbon in the middle and methyls on both sides. So that's actually an isopropyl unit. That would be something like, if you draw that out, we're saying it's PPH3 minus plus with two methyls on either side. So we actually bring a 3-carbon unit to the party, not just this one carbon. The correct answer is this P reaction. All right, now final stages. We take this molecule, we have an aldehyde. We're converting the aldehyde into this amino-cyano compound. That's our classic Strecker reaction. So we have to have ammonia, cyanide, and water when we do this one. So this is we're bringing together all the pieces that we have. Again, so we need to bring a nitrogen. We're not bringing hydrazine to the party or anything else. It's just simply the Strecker reaction conditions. After that, we're converting the nitrile back into this. That's simply acid, water, and heat. Something like this is how we would finish this one off in order to completely hydrolyze that center. Okay, so for this one, we're going to draw out the full mechanism in order to do this transformation. Now notice what you're doing, again, just to kind of target it. Really all we're doing here is this nitrogen, which is this nitrogen here, has to add to that carbonyl, which should be that carbonyl center over here. This is being done under acidic conditions, and also if you notice, we are starting with a secondary amine in order to make a secondary enamine. I just want to point something out to you because the comment I've made before. If you go through these questions in your test, it's possible to help with other parts of the exam, and this was done on purpose. If you look at a molecule like this, we have a carbonyl and a secondary amine, which is giving you a 6-membered enamine in the same conditions. If you go back, right here, acid conditions, secondary amine, aldehyde. This was set up to help get you sort of an idea that later on we're giving you the overall starting material and product, which gives you potentially a bit of help in that previous case. So do try to pay attention to these kind of features. There's parts of the test that can help you if you're unsure about other parts. So the mechanism we're going to do here is a condensation reaction. This is our standard reaction conditions where if, and again, you can open it in a couple different ways. I'll show you the way that we did it in our notes. The lone pair neutral is going to attack our carbonyl directly to give us a zwitterionic intermediate. And we've asked you to show all proton transfers, so we're going to do it longhand. So that's going to give us our O-, and like we said, this is a 6-membered ring, so I'm just going to draw this out where it's the nitrogen bent over to give you our zwitterionic component. All right, now this reaction is being done in the presence of catalytic acid. We've also got other acceptors like this other nitrogen, so there's more of these molecules present. You can say a base, or in this case, I'm going to use a second molecule of my amine in the solution to act as my catalytic base in order to capture that center. So it's going to do a proton transfer to give me the deprotonated form first. Or again, you could draw it where you protonate the oxygen first and then deprotonate nitrogen. Either way, what we have to do is 2 steps where we are satisfying the charge. 1, 2, 3, 4, 5, 6, sorry. 1, 2, 3, 4, 5, 6. Good. All right. So we have our methyl center across here, and we are going to have, let's see, our NRR. This is just another molecule of an amine from this. Another one of these basically is I'm just drawing as my base. And that's going to act as my source of my acid in order to get back to next stage. So that's going to give me back my tetrahedral intermediate, OH, methyl, like this. So now we're neutral. Okay, now next thing we're going to have to do is carry out some type of transformation where we have to get rid of this center over here. So this is where we're going to do another acid protonation. So some type of acid catalyst, we're going to protonate that center to help set it up to be a better leaving group. So we're now going to have OHH plus and N-methyl. And now that that's been protonated, we can use the lone pairs in this nitrogen to help to eject that oxygen. It's going to get us to our iminium intermediate. So we've got the 6-membered ring from previous. We now have our 6-membered ring, double bond to the nitrogen, and positive charge over here. And we've lost water effectively from that. So now, in order to finish this, to get to our final product, what we have to do is that center, this center over here, has 2 protons on it, and we're going to come back in with our base. Once again, it's either going to be the conjugate base associated with your proton over here. Once again, I'm just going to draw it as the amine. It has to deprotonate that center, give you a double bond over here, and slide the charge up over onto that site. So that's going to give us our final component where we now have a double bond between those 2 centers and a single no charge on the nitrogen anymore. Because again, this is our standard mechanism for enamine formation, part of the imine formation chapters we talked about at the beginning. Okay, here we're just asked first to fill out the reaction conditions to do this kind of synthesis. So we start off in this. This is sort of like a Horner-Wadsworth-Edmonds material. We've got a carbon center here. If you look at your product, this piece is retained. That's this fragment over here. That is our red carbon, and we're bringing in this new fragment over here. So we need to do 2 things. Step 1, we need to treat this with a base in order to deprotonate that center and make it nucleophilic. Second, we need to bring in our carbon fragment. In this case, it's a 4-carbon unit where we have a carbonyl in between that gives us this carbonyl is this carbonyl center here. And we're effectively, because we're doing it under HWE conditions, large group here and large group here are anti relative to each other. We end up with the E product. Okay, once we have that, we're going to carry out reaction conditions to give us something and something else to give us a product. So we're giving you here a work through where we have to actually kind of look forward for what's actually happening. Now, so this is what I'm just going to forecast. This carbon here is probably going to be, actually let me recolor them. The double bond we started off, that red one corresponds to the red carbon we had. Blue one is this one here where we've got that sort of fragment that corresponds to this piece. Counting out adjacent to it, this green one is probably this green one here, and more importantly, that pink one is this pink one here. Now notice what you've done is you've lost all of this chunk over here. You're missing this acetal kind of piece, and then more importantly, you're missing this chunk over here as well. So it's going to be a 2-step process where what we have to do is probably open up this acetal first, and then second, lose this CO2 or carbon dioxide in that part. So first step is just really acid catalyst. So it could be catalytic HCl, whatever, in water, right? So we need water present because we're doing a hydrolysis, If we do that, let me just draw out what that fragment would look like first. So the molecule, if I just was to cut off that fragment, should look something like, and if all I did is I'm just clipping off, let's say, those two bonds right there. So I'm not going to move anything else. I'm just going to do it the same way I would if this was an alcohol. I'd get this carbon out here. Now notice this is an enol kind of form, so I can redraw this as either that's our compound in the enol form or double bond up carbonyl, and I'm going to draw this as my OH, carbonyl down like this in that specific position. So now in the second point, as long as I have heat and make sure that we're under acidic conditions, we're set up to do our decarboxylation. That decarboxylation will first give us the enol form, which then tautomerizes to give us our final product. So now that we have to go through this, we're going to draw out the mechanism, and this is going to be done where we have PT or proton transfer to show the different parts. Now we're going to show first the Horner-Wadsworth-Emmons mechanism in each of the steps. Remember, we've got two stages. We have our protons. So the first correct one is we're using hydride as our base to form our Horner-Wadsworth-Emmons reagent first. O-methyl. And we can draw that as a negative charge or something that was stabilized. This is our first chunk. Okay, so now that we have the HWE reagent, we need to do a nucleophilic addition to the second molecule. Now remember, we drew that as this 4-carbon unit, so it's going to be nucleophilic addition to make our new bond. The geometry of that one you can express exactly, but most importantly, we have to show that we now have the whole molecule, our carbonyl, P, dimethyl, and we now have a new bond over to our second fragment. Excuse me, O minus. So after that step, this is going to be some kind of elimination reaction. We're going to get a phosphorus attaching over here, and in the process of doing that, you could probably draw it like this. So we're getting a phosphorus-oxygen bond in order to make our oxophosphatane. The geometry that we're trying to enforce here is that the two large groups are opposite each other. So during that oxophosphatane formation, we're going to end up with a 4-membered ring, phosphorus O, O-methyl, O-methyl, minus, just how we've drawn it, and we have an oxygen over here. Now, just to kind of emphasize it, we've got one group on one side of this 4-membered ring. It's going to be the main carbon fragment we've been dealing with, like this, and syn to that one will be the small group. In this case, it's the methyl. To the back is going to be our ethyl group. Now, when we complete this, the way we draw our arrows is a 2-2 sort of cycloaddition, or these two guys breaking, and that's going to give us our final product, which is, as we've drawn before, these two, carbonyl, double bond, methyl, and ethyl. Right, in the next step, we want to go a hydrolysis. So this is a hydrolysis of our acetal group. So we're under acidic conditions. We have water as well. So in order to kick this off, we're going to protonate one of those oxygens. I'm going to choose the exterior one first. That's going to give us our protonated acetal here. So you can draw that as simply a PT step, but now that we've protonated this one, what we have to do is effectively this SN1 kind of reaction. What we're doing as a result of that is, as a result of that, we're going to start this elimination process. So it's going to give us a positive charge over here, and double bond, carbonyl, OH. All right, now in this point, now that we have an electrophile, we're going to bring in water, and that's going to attack to give us next intermediate. This is now that sort of hemiacetal, this hemiacetal form up at this center. So we have our oxygen and OH. The rest of the molecule is still intact. Okay, so to eliminate that next point, what we need to do is, after that addition, it'll still be OH2 plus. We're going to undergo a proton transfer to get us back to our neutral structure. OH, bond, carbonyl, OH. All right, to finish this off, what we have to do is we want to break this final bond. So we're going to go through another proton transfer at that step to give you your OH plus and OH. And we're just going to basically eliminate that fragment. So that gives you this point. Now I'm just going to grab this one, and we're going to continue the mechanism. We've got a little bit more room. And okay, so now that we've done that, we're going to end up with our enol form of this product. OH, double bond, O, double bond, O, OH. So to convert it to our final product, we just want to convert this back to the keto form. In order to get to that one, what we're going to do is carry out one more series of proton transfers, the tautomerization, PT, where we're losing a proton here, gaining a proton over there. I could just break it up into two steps if we wanted, but effectively we're just one more final proton transfer to get us to our carbonyl, and I'm going to draw this in the right geometry for our next step. So that's this guy here. So for the final one, we're taking this, and we need to carry out two main things in order to complete this. First, we have a paracyclic reaction to produce our CO2. So it's our 6 electrons in one step in order to give us our enol product like this, and CO2. And finally, it's just a proton transfer to give us back one more tautomerism to give us the final product as we've drawn it, like that. All right, now just quickly for the bonus one, I'm not going to give you everything from this one, but I do want to give you a couple quick guidance. If you notice this molecule here, what we have to do is this fragment here is probably going to be that fragment through here. Sorry, I'm just going to highlight them again. So this part here is probably this part here. Now notice what's happened is carbons 1, 2, 3, 4, 5, and 6. Those make up carbons 1, 2, 3, 4, 5, and 6. So we have to install effectively this nitrogen while opening up this ring in some way. And the best way to do that is through a scission of this bond. This is our ozone under reductive conditions to get us to something like a dicarbonyl. Right, so we're going to end up with some type of dialdehyde structure. That's an important feature of this reaction when we do this. In order to do this, and for bringing these pieces together, well, I need basically this part here, and that's doing a reductive amination. Now, this could either be done up front or in behind. It doesn't matter which one you do, but basically you're going to need at some point either NH2 methyl, so you could make it this way, versus we could take ammonia, do the reductive amination. In fact, probably your best choice is to do the reductive amination first and then follow in this. The reason why is stopping at just this one without mono, di, or trimethylation is quite difficult. So we'd probably end up taking ammonia, doing 2 reductive aminations over here. Remember, reductive amination requires you to use something like sodium cyanoborohydride for that part. So I would generally do the ring opening. I would do a reductive amination between these to give you this kind of core function. Then I would follow up with that particular reductive amination there. That's how you build up that kind of ring part. Now, if you notice this fragment over here, the major things we have to consider is we've got this bromide. That bromide can be added nucleophilically. If you look at this fragment, these carbons here actually come from that fragment there. The problem is we've got to make this bond. That bond is going to be done if we turn this into an aldehyde first, turn that into a Grignard. We can add the 2 fragments together. That's going to give me a primary alcohol with the rest of your aromatic ring over here. Now, just in terms of order of addition, the Grignard addition here could be done first if you were before this ozone type thing, or you finish this ring and then do the Grignard. Halfway in between, where you've already exposed the aldehydes and then open up the Grignard, would be incorrect, because now you've got multiple electrophiles competing. So I'd either build up this ring first and then bring in the Grignard, or deal with the Grignard part first. But we can't do the ozonolysis quite yet. A molecule like this, what we have to do is finish off this capping here down at this part. Now notice what this is. That is a acetal. That acetal actually comes from this fragment here. This is actually an enol form. So under acidic conditions, you can actually convert this into a protonated form of that. I could draw it effectively like this, right? If I were to, protonate this ring in this way, so the way that that mechanism works, I would take these electrons down, go over, pick up a proton. That's adding like a proton like this to give me this oxygen plus. What that lets me do is take an oxygen like this and add into that center. So under acidic conditions, taking an alcohol like this plus a molecule like that will help us to form that acetal fragment. So those are the major components that I was looking for in this, plus the proper order of addition in order to get those fragments to be brought together.